Okay, here we go with other intermolecular forces. Your review will be on another video. With intermolecular forces, probably the one that comes to mind most often is hydrogen bonding. Now, hydrogen bonding basically has to have a nitrogen, oxygen, or fluorine directly connected to a hydrogen. So water works real well to show this. You can see that hydrogen is connected with blue dots to the oxygen. That means it's attracted. Now, if we look at this a little bit more, we can see that oxygen would take on a slightly negative side, so we get a little slightly negative on here, and the hydrogens would take on a slightly positive. If you haven't seen this sign before, it's a small delta, and so because of that, the slightly negative would be attracted to the slightly positive. This is a fairly strong bond, and some have even argued that it is a bond like covalent and ionic. But it's a bond, but it's not been agreed on by everybody as a bond. So just remember NOF with hydrogen. NOF with hydrogen will give you hydrogen bonding, and they'll rearrange. That's why ice will expand when it's frozen, is because it has to arrange positive, negative, positive, negative. It can't just go willy-nilly in there. Okay, another kind that we could talk about is network solids. Now this becomes really important. Network solids like silicon dioxide have a high melt or boiling point. Why? Because they arrange each other in lattices, so they're basically positive, negative, but they're a covalent bond. So because they arrange each other that way, they're become very, very strong, and they're most often 3D, with two exceptions. There's graphite, and graphite actually arranges itself in two-dimensional, so it's more like a sheet that has a bunch of carbons that are interconnected on this sheet. Okay, and we also have diamonds, and diamonds are three-dimensional, and three-dimensional carbon atoms like come out of the plane and attach to a carbon, come out of the plane and attach to a carbon, and go back into the plane, attach to a carbon, go back into the plane, attach to the carbon, come back out, attach to a carbon. So they're very 3D. And if you think about a really good 3D model that's not a diamond, but it's called a Buckminster fullerene, is like a soccer ball. If you took a soccer ball and at every place that it intersected on the soccer ball, the seams, and put a carbon, that would be known what they call a Buckminster fullerene or a buckyball. So you can get sort of a 3D model. Another type of bond is a metallic bond. This works with all metals. It doesn't have to be an alloy, but I've shown you an alloy here of brass. And what happens is the valence electrons are actually given off, and they move in what some people call a sea of electrons, but they move freely. They have mobile electrons. And so if you have mobile electrons that are moving around, then it makes it real easy to conduct heat and electricity. It also gives luster, because as light hits those electrons and they're excited, they give off luster. So a metallic bond is where we have mobile electrons. Think metals. That's why they conduct heat and electricity well. Okay, let's go back to ionic bonds for a minute. Ionic bonds don't conduct when they're solid, but they do when they're in solution or dissolved in water. That's because the bond between the two breaks. Remember, ionic bonds set up in a crystal lattice where it has Na plus and Cl minus and Cl minus and Na plus. And when I put it in water, this dissolves and becomes just an Na plus and a Cl minus in the water. And so because of that, it can conduct electricity when it's in solution. So we say that when it is put in water, the electrostatic bonds, which are this positive and negative, are dissolved. Okay, we have dipole forces, or dipolar forces is another one. I like to call them dipole forces. Your book calls them dipolar, same kind of thing. Basically, it's when we don't have a full positive, when we don't have a full negative, but one side is slightly positive and one side is slightly negative. Therefore, we have poles, positive and negative poles. So this little thing means slightly. That means slightly. It's a small delta. Most of you probably know delta from is a big triangle. Big delta would be like that, but we don't use the big delta. We use the small delta. And so we have slight positive and slight negative. Therefore, there is some attraction between these molecules. And this attraction is not as strong as the hydrogen bond. Okay, so you got to remember it's not as strong, okay, as a hydrogen bond, but it is strong. Okay, so we do get some effect. Now, because the hydrogen bond is strong, it will increase the boiling point and make it harder to get the melting point, because it has to arrange to a certain extent before it will finally freeze. Remember, it had to get the positive and negative together. So our freezing point will be lower and our boiling point will be higher because of that. Dipole forces do that to a smaller extent. Now, dispersion forces. This is the lowest melting, it's the weakest, but you got to be careful with this, because as the particles get larger, then the dispersion force gets greater and can actually overcome a dipolar molecule or dipole molecule. But for the most part, they're weaker. Okay, so you got to remember dispersion forces are weaker. And how this works is dispersion forces result from a momentary non-symmetric electron distribution around the molecule. Okay, what in the world? Basically, sometimes, if you look at this molecule over here, sometimes the electrons all end up on one side. And because they all end up on one side, we get a dipole effect just for a second. Because of that, then it's attracted to another one that is also in a dipole effect. So you can it's not real strong because it's not happening all the time. Okay, but the more electrons that we have around a particle, the greater chance that there'll be more electrons on one side of a molecule than on the other side at any one time. So then it'll be in a dipole situation more often. Okay, that's it for this chapter, so go to the exam number 4 video review.